very much, Robert, David. Thank you for the invitation to talk. So I'm going to talk about the work that we've been doing on these, on developing gene therapy, not just for immune deficiencies, but where that field is going as far as developing gene therapy for bone marrow disorders as well. And I've titled it The Development of New Genetic Medicines because there is a move to make these licensed medicines, and I hope I can show you how some of that is actually progressing, and that also plays into to what Robert was saying about the industrialization or the commercialization of these products as well. And in relation to that, some of the work that we've done has been incorporated into a commercial entity. So this is a slide that I drew up some time ago now. In fact, actually I didn't draw it, I just found the picture. But it was a slide that I made 10 years ago when it was about what could happen as far as gene therapy was concerned. What could gene therapy do for various different inherited genetic disorders? And actually, I wasn't trying to be prophetic, but all of these are now in clinic. So all of these have actually made it into clinic, and some of these are having really very dramatic effects. So I'm not going to pick all of them out, but there are now single administrations of an adenoviral associated vector that can correct hemophilia B and A. So a single administration of this virus incorporates itself into the liver and produces factor VIII or factor IX, and individuals are recombinant factor independent as a result of that one administration. That is a transformative change for that disease. An administration of a similar vector into the retina of the eye is able to restore photoreceptor function so that individuals have improved sight, again, as a result of this one administration. So there are really some very dramatic changes afoot as a result of these kinds of interventions. What we've looked at is correcting bone marrow disorders, and we started off with these severe immunodeficiencies, and again, single administrations of corrected bone marrow stem cells are able to correct an individual for their lifetime, and that is something that I'll demonstrate in my talk. But the expertise and the technology that has been developed in these severe immunodeficiencies is now being applied to other disorders of the bone marrow, including lysosomal storage diseases, of which there are many, and also hemoglobinopathies, which are not rare diseases at all, but of course affect thousands of individuals worldwide. And you'll also hear about how gene-corrected T cells are able to fight acute leukemias, and I think John will be talking about that later on. So this is where we started. We started with conditions with very high unmet need. And these are children with severe combined immunodeficiency, where a single gene defect in the bone marrow gives rise to a loss of the development of immune cells, or immune cells that develop but do not function effectively. And these individuals are susceptible to all kinds of different infections, bacterial, fungal, viral, and these children will die in the first year of life without any effective intervention. The molecular defects that lead to these conditions have been now identified, and numerous genes have been identified, and they give rise to abnormalities of development of these progenitor cells. And I'm going to talk about two specific molecular defects. This is the common gamma chain, which gives rise to the X-linked form of SCID, and the ADA gene, which gives rise to the ADA form of severe combined immunodeficiency. And together they form about 40 to 50% of all the different types of severe combined immunodeficiency. And these are the two genetic forms where we have targeted gene therapy. Now, the conventional treatment for these conditions is a bone marrow transplant. So an allogeneic bone marrow transplant, taking marrow from a matched, or in some cases not so well matched donor, and giving it to these individuals. And where we have a very well-matched donor, usually a sibling, or in some cases a family relative, then we can get over 85 to 90% survival. But when you use unrelated donors, or you use mismatched donors, or family donors who are mismatched, then the survival rates are much worse. And even now, even in the best case scenario, we would say that a bone marrow transplant still has a 10% mortality. In cases where you use unrelated, it would be about 15 to 20%. With mismatched, it's down to 25% or so. This is historical data from Great Ormond Street. Why use gene therapy? Because you have the perfect match. It's the child's own cells, can't be rejected, can't give rise to graft versus host disease, which is the major problem with allogeneic transplant. Also, in these conditions, we can give gene therapy with significantly reduced amount of chemotherapy. So we avoid the short-term and the long-term toxicities associated with chemotherapeutic conditioning. So we think this was going to be a safer procedure, but can it be as good in terms of promoting immune reconstitution? And so this is the condition that we started this at. This was the first condition, the first monogenic condition that was ever corrected by gene therapy. And this is a disease where it's the X-linked form of SCID. It's a defect in a cytokine receptor complex. So this is a subunit of the cytokine receptor complex for actually a number of different cytokines, IL-2, 4, 7, 15, 21, and it gives rise to severe immune deficiency. As a result of this, T cells don't develop, NK cells don't develop. The idea is really, very simply, take bone marrow stem cells, introduce a working copy of the gamma chain gene into those stem cells so they now have the correct signal to be able to develop T cells or NK cells. The kind of biomarker of success is very simple. These kids start off with no T cells, and therefore, if this works, we should see T cell reconstitution. And that is what we saw. So here in this trial, which we started in 2001, 10 patients, we took stem cells, we introduced a working copy of the gene into those cells using a disabled virus, and then we returned those cells back to these patients without any chemotherapy conditioning. In fact, some of these patients were almost treated as outpatients. They received their treatment and they went home again. We followed them up as outpatients. So all of these patients start off with very few T cells, and as you can see, all of them have increased T cell recovery. Now, this has been published a long time ago, and we've shown that those T cells are functional T cells in terms of proliferative capacity, in terms of their repertoire, in terms of going through thymic reconstitution. So this was very successful, held a huge amount of hope for other diseases. A similar study was conducted in Paris by Alain Fischer and Marina Cavazzano, which showed very, very similar results. First patients, as I said, in Paris were treated in 1999 at Great Ormond Street in 2001. In 2002, there came these adverse events, these leukemias, in patients in Paris. In 2 patients in Paris, they were identified as having leukemias, and they were T-cell ALLs. When these were investigated, it was found that the leukemia, the initiating event in the leukemia was as a result of vector integration. So these vectors integrated into the genome, and what was found in these leukemic clones was the vector had integrated near a known proto-oncogene known as LMO2. The vector had turned on LMO2 in a non-physiological fashion. That had driven the abnormal cell cycle in these cells, which had then accumulated other genetic lesions and gone on to a transformative event. But the initiating event was the turning on of LMO2 by this vector. So obviously this caused a huge amount of problems for the field. It set the field back. These vectors, which we thought would be able to promote immune recovery, were giving rise to these kind of adverse events. And a lot of work went into understanding why that was actually the case. And this is the design of the vector. This is the vector that was causing the problem. So these are taken from gamma retroviral vectors. The inherent genes of the vector are stripped out, and we put in place a transgene that we want to express this common gamma chain gene. But the promoters are still the promoters of the gamma retrovirus, and they have these long-term repeats, which have powerful enhancer sequences. So when this vector sits next to an oncogene, these enhancer sequences are able to turn on the neighboring gene. And in the case of LMO2, it was turned on in an aberrant fashion. So an awful lot of work went then into redesigning these vectors. In fact, some people just said, we're not going to touch this any further, but others went on to say, well, can we redesign these vectors? And that's what happened. So we went in to design vectors where these LTRs were now deleted. and were no longer active. Those enhancer sequences were removed. You still have to transcribe your gene, so you have an internal promoter that now allows transcription of the gene. And then in vitro studies, in vivo studies were performed in head-to-head comparisons, which showed that even if these vectors, this new design of vector, if it sat next to an oncogene, it couldn't turn the oncogene. So in vitro models of transformation, in vivo models of transformation, the transforming capacity of these vectors was significantly lower than these vectors. So we then went back into clinical trials using this new design of vector. The backbone vector was actually changed as well. We used gamma retroviral vectors in early studies, but we went to lentiviral vectors for future studies. So the lentiviral vectors based on HIV-1. So in this study, using a gamma retroviral, but with a new design, with this self-inactivating design, we were able to see, again, immune reconstitution that was very similar to what had been achieved previously, but now 6-7 years after the first patient had been treated, there have been no clonal proliferations, there have been no expansions, there have been no leukemias. And if we look at the molecular signature in these patients, we can't see any evidence of clones emerging with insertions and integrations near LMO2 or other oncogenes. So it seems to be considerably safer than the vectors that we had been using previously. Now, this is the other condition, ADA deficiency. So this is a condition, again, it's actually a metabolic disease. ADA is expressed in all body cells. But in hematopoietic cells, as you break down your DNA, deoxyadenosine has to convert to deoxyadenosine. ADA catalyzes that step. In the absence of ADA, it builds up deoxyadenosine and also deoxy-ATP, which are toxic to lymphocyte proliferation and maturation. We had actually done a gamma retroviral vector study with this disease, in this disease first of all, with some success, but with the adverse events that had been seen in X-linked SCID and actually in other immune deficiencies, we decided to go to a better, safer vector format. And so we designed an HIV-1 vector where we strip out the HIV genes, and we now express a codon-optimized version of the ADA gene under the control of a cellular promoter. So these promoter elements of HIV have been deleted. We took this into in vivo systems. We were able to show reconstitution in a murine model. We showed that T-cell development, B-cell development was equivalent to that using other vectors and also due to standard transplants. We then undertook an in vitro study where we look at transformation potential of this vector. And essentially what this involves is taking murine stem cells, infecting them at a high copy number with your test viruses, and then growing them out and look to see whether they actually have the capacity for transformation. With the old vectors, we could see a high level of transformation capacity, but we couldn't introduce any transformations with the vector that we had developed. This was then taken into clinical studies. We developed this with a group at Los Angeles, at UCLA, but with the same vector using very similar protocols. We conducted a study in London and a study at UCLA. Endpoints were survival at 2 years and also looking at immune reconstitution. The vector was made to clinical grade at the Indiana University Vector Production Facility. These are now the results from both London and from UCLA. And these are the geometric means of now 30 patients that have been treated between the two centers. So when we put this together, we had no idea how closely the reconstitution would actually overlap between the two centers. But you can see in blue from the US and green from the UK, you can see the T-cell reconstitution in these individuals, in CD4s, in CD8s, and in CD19s as well. What happens to these patients as far as their clinical outcome is concerned? All of these individuals come into the procedure on enzyme replacement therapy. So we then give them the gene therapy procedure, and then we stop enzyme replacement, and we look for immune reconstitution. So in fact, in all the US patients, they've all been able to stop enzyme replacement therapy, and only one of the patients treated in London has had to go back onto enzyme replacement. So in terms of efficacy, it's been extremely encouraging. So this is as a result of that one-off gene therapy procedure alone. They've got T-cell reconstitution, they've got B-cell reconstitution as well, and in fact, these patients are all stopping or are scheduled to stop immunoglobulin replacement therapy. And the one patient had to go back onto enzyme replacement therapy is also the one patient who has remained on immunoglobulin replacement. So we've got both T-cell recovery and we've got B-cell recovery as well. Now, we don't often see survival curves like this when we do transplantation, but this is the kind of survival curve that you want to see. So all of these patients have survived this. It's not a curve, it's just a flat line, so it's good. Now, if we'd done a conventional, if we'd put these patients through an unrelated donor transplant, which would be an alternative, it's about 70% survival. So we've got a stage now, October 2016, 40 patients treated. Now, that isn't, for those of you in more common diseases, that sounds like a very, very small number. For the kind of disease we deal with, that's a big number. So 40 patients treated. Survival, all of those have survived. One patient back onto enzyme replacement, no evidence of persistent clonal dominance individuals when we look at molecular marking. Where do we want to take this? Well, we wanted it to be a standardized therapy. We want it to be a standard therapy when children do not have a matched sibling donor available. These kind of guidelines we've put together with gene therapy now as the standard treatment if no matched sibling donor is available. So we can do this for X-linked SCID, we can do this for ADA SCID. There are murine models that have been corrected for other forms of SCID as well. So there's recombination defects, RAG1, RAG2, and Artemis. There have been murine models that have been corrected, and those are now going to be taken forward to clinical studies. So there will be a gene therapy option for all the different forms, or the majority of the different forms of severe combined immunodeficiency. I'm just going to talk very briefly about another condition as well, chronic granulomatous disease. This is a condition where neutrophils form, but they do not have the functional NADPH complex to be able to kill bacteria effectively. And this component gives rise to the X-linked form of the disease. Again, we've taken that forward with a novel vector that has been developed in our lab. There is now a conditioning protocol in order to make space for gene-corrected cells. I'm just going to skip that and go to this patient here that we treated last year. These are all the clinical problems that he had, significant clinical problems. This child was on intensive care 3 years ago. We were thinking about whether we should continue treatment or just stop at that stage. He recovered from that, fortunately, and then he went into this procedure. And last July, we took cells, we corrected them, we gave him chemotherapy, we gave those cells back, and now, 8 months after the procedure, he has 31% functional neutrophils in the periphery. He's been able to repair his anal fissure, he's gaining weight for the first time, he has cleared infections from his chest and is going back to college. And that's been repeated in 4 other patients worldwide now and is going on to a much larger study. This is a slide not prepared by us, but prepared by Alain Fischer in Paris, where he shows the number of patients that have now been treated. We have 130 patients in different immune deficiencies. The overall survival is over 95% with excellent efficacy in those populations. These are trials that have been conducted in the US and also in Paris as well. Finally, just to say, this is not just for immune deficiencies, but is now going on to treat metabolic diseases, and also in the New England Journal that was just a couple of weeks ago, gene therapy, bone marrow gene therapy for a patient with sickle cell disease. There's a whole list of diseases that are amenable to this form of gene therapy: immune deficiencies, lysosomal storage diseases, and hemoglobinopathies as well. These are the first cures for specific SCID conditions and metabolic conditions as well. They were the first cures with gene therapy. The mortality and the morbidity, when you think of the kind of innovations that we've seen previously, are extremely low. How did bone marrow transplant start? How did organ transplant start? What were the mortalities in those early studies? And if you compare that with the kind of mortalities and morbidities that we're seeing now, it's extremely low. We still need safer vectors. We still need to look at individual, the way those genes are regulated before we go into clinical studies. This can be done in an industrialized fashion whereby cells are taken rather than patients, and cells are taken to central manufacturing facilities, corrected, cryopreserved, quality control and conducted, and then cells shipped back to patients to be infused at the bedside. Will they be future gene therapy medicines? There's already a gene therapy medicine like this. So GSK have actually taken one of these products, a gamma retroviral vector for ADA, from Milan, and that has got approval as a licensed medicine. There are a number of other industrial entities that have formed who are trying to do this for beta thalassemia and sickle cell, for lysosomal storage diseases, for Fanconi's anemia, for other immune deficiencies as well. And so I'd like to end there and just really thank the enormous group that I've been able to do this, both scientists in the lab, our clinical nurses, our clinical colleagues, and also a huge number of collaborators worldwide, including this excellent collaboration with UCLA. And that's my partner, Adrian Thrasher, with whom I've worked over the last 20 years, bringing these to the clinic and to the funding bodies who have supported us. Thank you very much.
Terrific. It was fantastic work, Bobby. Thank you very much, and really clear. And just to reinforce the point you made, I think Roger Williams may correct me, but I think Tom Starsel's first 6 liver transplant patients died, and any normal ethics committee would have shut the program down. Fortunately, they didn't. And it's now a treatment. Different times, yeah. Okay, a few minutes for questions. Could I just kick off with one, which is, to what extent are these kids chimeras in terms, so I don't know how severely you condition them. So do they have their defective stem cells producing some lineages? And
so there's a very powerful survival advantage for gene-corrected cells. So in the periphery, all their T cells are gene locked. They wouldn't get T cells if they didn't have a gene in them. So that's also the case in other lineages as well. So in lineages where there's not a powerful survival advantage, it is a mixed chimera. So for example, in the B cell lineage in X-linked SCID, it's part gene-corrected and part not gene-corrected. But because there's no dominant effect of the negative population, then that doesn't seem to matter. In the bone marrow, it's variable, but it's anywhere between 10 to 30% CD34s in the bone marrow are gene-corrected, but as they develop into H3, the survival advantage, it becomes a full lineage correction.
the rules have changed. I don't need to write down the names of people asking questions without them telling me who they are. That was days gone by. Sanjeev.
Thank you very much. That was lovely. Just a quick question that I think reflects probably the impatience of the families that you have to deal with, as well as the wider community. How long will it be before this sort of approach that you've described will become the standard of care, against which, for example, bone marrow transplantation becomes a second-line intervention? How long do you think you need to wait, and how many numbers do you need to accumulate before that happens?
It's a very interesting question. So, I've worked with my bone marrow transplant physicians, and we work very closely side by side. When we first started this, there was always a bit of a skepticism about whether we should be doing gene therapy when we had a bone marrow transplant option. Now, when we come to discuss a patient, they say, why can't we do gene therapy? These results, when they see how safe it is, when they see the efficacy, so obviously it has to go to the regulators. And then we'll put the evidence, as we're doing, we'll put the evidence before them. These are the outcomes with a contemporaneous cohort of BMT patients. This is the gene therapy cohort, which should be the preferable choice. So once that decision is made by regulators, then we'll know what is the standard of care.
Liz Simpson.
Elizabeth Simpson. The cases in the children that you're speaking of, you would expect perhaps a tolerance to be induced in them, because those cells will be in not only bone marrow but thymus and through the body. However, the factor 9 case that you mentioned, you're putting that material into adults and you're not affecting the rest of the immune system. And this is the factor 9 that's being produced by gene therapy is in fact a foreign protein. What evidence is there of that being tolerated?
In fact, there is a problem as far as that is concerned. So there is still an issue about tolerance to that new protein. And those individuals have had an immune reaction to the new protein, and also to the AAV vector that is brought in that carries that gene into the liver. So there's a lot of, so there have been individuals who've had quite high transaminitis as a result of that, because the protein is being expressed in the liver. And so they've had to have some immunosuppression in order to damp down that reaction. So there are, I mean, I'm not involved in that kind of study directly, but I know the investigators are looking at ways of trying to induce tolerance in those studies.
Farah, could you introduce yourself briefly?
Basson Down, Newcastle, visiting Imperial. This may be a very stupid question, but as I understand it, the LTRs are very similar to mobile genetic elements, and our genome is sort of riddled with graveyards of retroviruses. So what do you think about 20 years down the line? I mean, do you think that there will be more instability in the genome in these cells? Because, I mean, you did say you inactivated the LTRs in your initial ones, but I wasn't sure whether in the lentivirals the long terminal...
Yeah, so those are inactivated as well. So those are deleted sequences. Right. So those are no longer active.
Right, so there's no possibility that they're going to be recombination.
And there are lots of mutations that are introduced into those vectors, so the chances of recombination events and creating replication-competent virus is significantly diminished. And that's one of the safety things that we have to do, is to look for replication-competent virus. And in all the laboratory studies and in all the patients that have been treated, there's never been any evidence of replication-competent either retrovirus or lentivirus being generated.
I wasn't really meaning competent replication. It's more that the long terminal repeats can behave like mobile genetic elements and move around, so that you might get chromosomal instability, in 20 years down the line or 40 years when these children are...
I don't think that's ever been, that hasn't been looked at in any significant detail. Right. But I don't know how mobile those elements actually are.
Steve Smith, who's on the board of Great Ormond Street.
Hi.
Oh,
yeah, hi. Can I just, it's a very simple question as well. Your titers are still going up there. Have you reached the stage when the titers begin to go down again and the clones get less and less? And would you need to sort of re-inject or
yeah. So our first patients are now 16 years after treatment. And so actually after about 2 years or so, there is a plateau in that T-cell development. And in fact, we haven't seen any diminution of that over that time. So, and I think that's because we've actually corrected true progenitor cells, if not true stem cells. And so there's a renewing population of gene-modified cells that is continually replenishing the immune lineages.
Final question. Oh no, Michael as well. 2 more. Yep.
Mark Lippman, London. Great talk. I'm interested in the cost of it. My guess is this is really cheap. Relatively.
You're cheap, aren't you?
So it's difficult to know. So actually, the one marker that we have is GSK have made this vector, have made this treatment available, and that costs 594,000 euros. Now, whether other people will charge similar amounts or less, we don't know. And it hasn't yet been approved by NICE and by the NHS for reimbursement. So these are now test cases, really, as to what this will actually be priced at. I mean, it's actually going to be difficult because we're used to medicines that are being given on a regular basis, and that's how commercial entities make their money. What price do you pay for a single intervention that's going to cure an individual for life? We don't know the answer to that, and that is a debate that will. There's an academic and clinical value, but what is the commercial value and what is the value to the NHS? And that debate is happening now.
Michael Schneider.
2 quick questions. Terrific presentation.
Whoa, short.
Quick. The quick one is, you described beautifully the evolution of the vectors in terms of safety from the point of view of insertional mutagenesis, but in Jim Wilson's early trials at Penn, the safety issue was an acute inflammatory response to the vectors. And could you comment on how that aspect has been engineered over time?
So in Jim's study, the Jesse Gelsinger case, that was a high dose of adenoviral vector that was infused systemically into the individual. So that kind of approach has now been tempered by the use of other vectors such as AAV rather than adenovirus, by the use of dosing schedules that are significantly different from what Jim used as well. So those have been built into trial development.
And the other question relates to muscular dystrophy, which was one of the features of your cartoon from 10 years ago, but which has been notoriously difficult from the standpoint of forcible expression of the wild-type protein. Could you just comment on what you see as the direction of travel in muscular dystrophy?
Yeah, I think that's difficult just because of the complexity of correcting large different muscle groups. And of course, there's the exon skipping approach that has been used using antisense nucleotides that has been developed both and has now actually been licensed for use. So I think that is still limited in the level of efficacy that it offers, and I think people are obviously looking at AAV that will then transduce large amounts of muscle, but that hasn't yet gone into clinical trials. But I think a more systemic approach is required if we're going to get multiple muscle groups corrected.
Chairman's prerogative, one last question, slightly facetious. So I noticed in the ADA trial that the CD45RA counts went down in the English cohort, and in the Indiana cohort they went up. So is that because the UK are dirtier and therefore we're getting more memory and switching from naive cells faster?
We've looked at CD45. No, so when we've looked in both the UK and the US cohort, and we start looking at more specific markers, we've done track analysis, etc. These patients who don't have any evidence of thymopoiesis start to reconstitute thymopoiesis as a result. So we can present more detailed data at a later stage, but there is reconstitution of thymopoiesis.
Okay, well, thank you so much. Really great talk.